In this video, I'm going to introduce you to partial derivatives. So let's say you've got a surface given by this. So the origin is right here. This is your x direction. So this is positive 1. Imagine this is positive 1, positive 2, positive 3, and so on. This is negative. So negative 1, negative 2, negative 3, and so on. And this is your y-axis. This is your y-axis. So y is positive 1, positive 2, positive 3, and so on. This is negative 1, negative 2, and so on. So let's say you've got a plane, a vertical sheet of paper. So imagine you've got a vertical sheet of paper, a vertical plane. Hang on. So hang on. Let me just draw my vertical sheet of paper. Let me just draw my vertical sheet of paper. Hang on. So I've got my vertical sheet of paper. I'm just going to move it down slightly. Hang on, move it down slightly. So the origin of my vertical sheet of paper is here. This is the x-axis, and this is the y-axis. The y-axis is along here, but I don't care about the y-axis. I just want to know the z-axis. So let's just say the z-axis looks something like this. Okay, so now I'm just going to move my sheet of paper along y equals 2. So it could be anywhere. I just want to illustrate it at y equals 2. So at y equals 2, hang on, at y equals 2, keep an eye on the origin. At y equals 2 is going to be 1, 2. So just imagine 2 is here. Just imagine 2 is here. So where the vertical sheet of paper intersects with the surface, you're going to get something like this. You're going to get something like this. So where the you've got to forgive my drawing. So where the vertical sheet of paper intersects with the surface will look something like this. You've got to forgive my drawing. So this is hang on, so now this is your z-axis and this is your x-axis. Don't forget this is positive here. So positive 1, positive 2, positive 3, negative 1, negative 2, and so on. Because here we're in 3D, so it's, you just got to accept it. So x in the positive direction is in this direction, and well along y equals 2, along y equals 2, you can put this 2 into the y here, So the equation for this curve would be given by z equals, remember we're putting the 2 into the y here, so this thing here would become 2 squared would be 4, 4 times 2 would be 8, so 8x, and then put the 2 into this y here, so that would be 2x to the power of 3. So the equation for this curve is given by this thing here, and now you have the right to work out the gradient along here. You can work out the gradient by treating this y as a constant. So if you want to, you can work out the gradient right here. If you want to, just differentiate it. So dz by dx equals, remember y is treated as a constant. So along this plane, along this particular vertical sheet of paper, y is a constant. Y is simply 2. So you can differentiate it. So differentiate it. So that would be 8, and then this would be minus 6x squared. So if you want to know the gradient right here, you can just differentiate it. So you can just treat y as a constant. What I'm trying to illustrate here is this. Hang on. So remember our surface. Our surface is given by this. Our vertical sheet of paper. Hang on. Let me just redraw the vertical sheet of paper. Something like this. And then we would move it down. The origin is somewhere around here. So this is our vertical sheet of paper. If we move it along 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 y equals 3 this time. So let's move it to y equals 3 this time. So y equals 3, bear with me, let me just erase this, and then I'll move it along, keep an eye on the origin here, move it along y equals 3, 1, y equals 1, y equals 2, y equals 3, and then where the sheet of paper intersects with the where the vertical sheet of paper intersects with the surface, you're going to get something looking like this. If you move it to y equals 2, you're going to get a surface. Well, you're going to get a curve looking something like this. And then in both scenarios, you have the right to work out the gradient. If you really want to know the gradient along here, you could work it out. You could just differentiate this. So this would be dz by dx equals 16 minus 27x squared. But the point is that we would use what's called partial derivatives. So we would invent a new notation. It's written as this: partial derivative with respect to x would be given by this. So given this, if you want to, so rather than looking at every single scenarios of y equals 2, at y equals 2, and then at y equals 3, at y equals 4, at y equals 5, and so on, we would just invent this new notation here. So just when you come to partially differentiate it, treat y as a constant. So treat y as a constant. So this thing here is just a constant, and then this is a constant. So merge these two together. So when you partially differentiate this with respect to x, then x is the variable here. X is the variable. This is a constant. This is a constant. So when you differentiate it with respect to x, it's just going to give you 2y squared, because y is a constant. So when you partially differentiate it with respect to x, this thing here, remember we are partially differentiating it with respect to x. That will then become this, and now differentiate this partially with respect to x. So this thing here is a constant. So when you differentiate it, the 3 will come down. That will give you 3. That will give you 3. Hang on, I think I've made a mistake here. Hang on. Yeah, I made a mistake here. Sorry, hang on. Bear with me. This should be. Bear with me. Hang on, bear with me. Let me just. How do I erase this? Bear with me. Let's start again here. So when you partially differentiate this with respect to x, this is a constant. This is a constant. So it will then become 2y squared. And then when you come to differentiate this with respect to x, so y is a constant, so that would be minus 3x squared y, because y is just a constant. So when you partially differentiate this with respect to x, it will then give you this. Okay, I made a mistake here. Okay, so hang on. So when given a surface, when you partially differentiate it with respect to x, you've got to treat this as a constant. So this is a constant, this is a constant, this is a variable here. So merge these two together, that will then give you this, and then this is a constant, this is a variable here. So the 3 will come down, the x stays intact, the power gets minus by 1, and don't forget y is a constant. So when you partially differentiate it with respect to x, it will give you this. Now you can use the same argument with respect to y as well. With y, you're just imagining a plane along. Let's say you're imagining your sheet of paper like this. So the origin. Let me just move it down. So this is the origin here. With respect to y, you're moving it depending on where you want to move for the y. So you can use the same argument, but in the y direction. So when you come to differentiate the surface, when you come to differentiate the surface with respect to y, so now this, you've got to treat x as a constant. You've got to treat this thing as a constant. So let's try and differentiate this. Remember, x is a constant, y is a variable. So the power comes down. That will give you 4. X is a constant. Y stays the same. The power gets minus by 1. That will then give you this. So if you differentiate this, if you partially differentiate it with respect to y, it will then give you this. Now, y, this x here is a constant. Y is the variable. So when you come to differentiate this part, it will just simply give you this, because this is a constant. I hope you get the gist of it. Okay.